Hello again, and welcome to our first flipped geometry class. I'm really excited about this. Hopefully this works out well. What we're going to be talking about today are points of concurrency, specifically the circumcenter, incenter, centroid, and orthocenter. So get out your notes and let's get started. Now we do need to remember some old words today, like the perpendicular bisector. This is a segment, a line, a ray, or a plane that is perpendicular to a segment at its midpoint. And what that means is that this segment is cut into two equal pieces. Now there is a theorem that goes along with this for us today. It's the perpendicular bisector theorem. In a plane, if a point is on the perpendicular bisector of a segment, then it is equidistant from the endpoints of the segment. So what that means is that this point P, up here, there we go, is equally distant from point A as it is from point B. So those two lengths, those two distances are equal, they are the same. Alright, here's a good example of cross-curriculum standards. We're going to take an English word, concur, which means to be of the same opinion or to agree, and we're going to kind of give it a geometric twist. So in English, we could say if people concur, then they have the same point of view. Now, geometrically speaking, whenever we talk about concurrent lines, what we're talking about are three or more lines that meet at the same point. And the point at which they meet is called the point of concurrency. Give you a second here to write all that down. Alright, now here's a good illustration of the point of concurrency. The blue line, the green line, the red line, they all meet at this central point right here, the point of concurrency. Alright, now there is a theorem that goes along with the concurrencies of the perpendicular bisectors of a triangle. The perpendicular bisectors of a triangle intersect at a point that is equidistant from the vertices of the triangle. Now when I say vertices, I'm talking about the points of the triangle, the three corners right here, 1, 2, 3. Now the blue line represents the perpendicular bisectors, and the red lines represent the distance to each vertex, and what this theorem is saying is that those distances are all equal, so all of those red lines are the same length. We do give a special name to the concurrency of perpendicular bisectors. We call it the circumcenter. So that's this point right here, the circumcenter. Let's make that big and bold. There we go, circumcenter. Ta-da! One neat thing about the circumcenter is that it will always be the center of a circle that you can draw that goes through each vertex of any given triangle. Now it is kind of interesting to note that on an acute triangle, the circumcenter will always be inside the triangle. On a right triangle, the circumcenter will always be on the triangle, so it'd be touching one of the sides. And on an obtuse triangle, the circumcenter will always be outside of the triangle. So it's kind of a neat tidbit there. Okay, here's another old word that we need to remember, an angle bisector. This is a ray that divides an angle into two congruent pieces. And remember, that's what these little swish marks mean, is that they are congruent. So we have a theorem, the angle bisector theorem today. It says if a point is on the bisector of an angle, then it is equidistant from the two sides of the angle. So this point D right here, it's sitting on the bisector. So that makes it the same distance away from this point, this side, as it is from this side over here. And that's what these two little blue lines show, is that they're the same distance. Alright, so we have 3 angle bisectors in a triangle. So another theorem that we have today, it says the angle bisectors of a triangle intersect at a point that is equidistant from the sides of the triangle. And that's what these little red dotted lines represent, the distance from that central point to each side of the triangle. Now this point has a special name also. This is called, as soon as I find it, there it is. This is called the incenter. Something interesting about the incenter is that it will always be inside the triangle, no matter what kind of triangle it is. And this is kind of easy to remember if you notice the ins on the inside and incenter. Now, another interesting thing is that the incenter will be the center of a circle that you can draw that touches all 3 sides of the triangle. Now, the median of a triangle is a segment from the vertex to the midpoint of the opposite side. So when I draw this, I usually start at the midpoint. So let me draw this one for you guys. We're going to start here at the midpoint, and we're going to make a line to the opposite vertex. And there we go. And we're going to do the same thing with this one. Start at the midpoint and go to the opposite vertex. And one more. And there we go. Those are medians. Now here's a little spoiler for you. The point of concurrency for medians of a triangle is a centroid, so I went ahead and named this one the centroid theorem. What it says is that the medians of a triangle intersect at a point that is 2/3 the distance from each vertex to the midpoint of the opposite side. Okay, so that's an awful lot of words. So I kind of summed it up here using this picture and these formulas. So what we're saying here is that of this entire segment right here, AE, 2/3 of that segment is housed right here in AP. So that leaves 1/3 of the length to be in this segment from P to E, and we'll mark that with blue right here. So to kind of sum this up, the 2/3 length is this side over here where the vertex is, the red side, and then the blue side is 1/3. And that's true for all 3 of these medians. Now this is the part that we've already talked about. The concurrency of medians is called a centroid, and that's this point P right here in the middle. There it is. And that's the centroid. Alright, so an altitude of a triangle is the perpendicular segment from a vertex to the opposite side, or the line that contains the opposite side. So this over here is the first case, where we start at the vertex and then we go straight to the opposite side and we intersect that side at a 90-degree angle. Now on this triangle over here, the opposite side would be this one over here, and obviously we can't make a line that connects and intersects that side at a 90-degree angle. So what we do, we extend that side and then we make a segment that intersects that line at a 90-degree angle. And that's the second case. The last theorem we have today is about the concurrency of altitudes of a triangle. What this says is that the lines containing the altitudes of a triangle are concurrent. Now, we call this concurrency the orthocenter. So that's this point right here, where those three lines meet. So what I'd like to leave you with today is kind of a summation of all of the new vocab words that we have gone through. And I find that this next chart is a very efficient way to store your notes. So here we go. What I've done here is listed the types of lines that make up each of these pictures, that make up each of these concurrencies, and then I gave you the specific name for each of those concurrencies. Now, these pictures did come directly from the screencast, so if you find that they're too small, you can always back up. Also, the word median and altitude, those are relatively new, so in this chart I would probably make a special note giving their definitions. Alrighty, well, that's all I got. So thank you for your time and have a great weekend.